Okay, standard conditions. It's useful to have kind of a reference point for comparing gases because they have so many parameters, volume, temperature, moles, pressure. It gets a little confusing to compare them. So standard temperature and pressure, also known as STP. Standard pressure is 1 atmosphere, which is equal to 760 torr. Standard temperature is the freezing point of water, 0 degrees Celsius or 273 Kelvin. Those are convenient because they're easy to obtain. Remember that most of these gas experiments were done back in like the 1700s. They didn't have electricity. Primitive conditions. You can achieve 1 atmosphere of pressure very easily. You hook up a manometer to your container and you adjust the pressure so that the levels of mercury on both sides are the same. Not super exact because you may not know exactly what the pressure outside is, but it's going to be really close to 1 atmosphere. So that's easy to obtain. You want to set the temperature of your flask, put it in a big container of ice water. Wait a few minutes, it's 0. So that's why we use that temperature and pressure. It's just useful for making comparisons. So we've talked about molar mass of things, right? That's the mass of 1 mole. The molar volume of a gas is the volume of 1 mole. The molar volume of a gas at STP. How much volume 1 mole of gas occupies at STP? Does this 273 bother anybody else? What should it be? It should be 273.15. There, that's better. Let's calculate the volume of 1 mole of gas. So at STP, we've got the temperature, we've got the pressure. N is equal to 1 mole because that's what we're calculating. So this is going to be an exact number. These are essentially exact numbers as well. So let's see. PV equals nRT. So the volume is going to equal nRT divided by P. So N is 1 mole. What's R? 0.08206 liters, atmospheres per mole, Kelvin. Temperature, 273.15 Kelvin. Oops. What's the pressure? 1 atm. Check the units. Moles and moles, atmospheres and atmospheres, Kelvin and Kelvin. So the volume is 22.41 liters. That looks confusing. 1. For 1 mole. 1 mole of gas occupies a volume of 22.41 liters at standard temperature and pressure. Gases are very difficult to measure by weighing them because they float away, right? They float away. But you can actually measure gases by their volume at a particular temperature and pressure, and so that's much easier to do than masses. So this is a useful number to remember. The molar volume of any gas at STP is 22.4 liters per mole. I do not know why they round it to 3 sig figs, but they generally do, so we'll just deal with it. So Avogadro's number of molecules or atoms of a gas, any gas, at STP will occupy a volume of 22.4 liters. 22.4 liters is a cube with a side about this long. So it's like, a good-sized packing box, right? That you might pack blankets or something in if you were moving. What the gas is doesn't matter. because the gas particles are so far apart from each other that the size of the particles doesn't matter. They're going to have different masses, those volumes of gas, but their volumes and the number of particles will be the same. This makes a very useful conversion factor. So molar volume in STP illustration. 1 mole of helium at STP occupies 22.4 liters. 1 mole of xenon, 22.4 liters. Which do you think is larger? They kind of did it in this picture. The xenon atom or a helium atom? Xenon's much larger. Look at it on the periodic table. A helium atom has two protons and 2 electrons, weighs 4 atomic mass units. Xenon, 54 protons, 54 electrons, 131 atomic mass units. Much, much larger. Still occupies the same amount of volume. The size of the molecule doesn't matter because they're so spread out. We've gone on some family vacations. We drove through Wyoming. Beautiful place. Population of the state is about the same as the population of Fresno without Clovis. In the whole state. The size of the people doesn't matter at all compared to the vast amount of space. Now, you put people in an elevator, right? You put 10 people in that elevator. I don't know if you've been in that elevator. You put 10 people in there. It's going to matter if those are little kindergartners or if it's the linebackers from the Fresno City football team, right? Because it's a close space. You're touchingly close. Now the size of the particles matters a lot. You spread out over the area, the volume of Wyoming, it doesn't matter anymore. In gases, the sizes of the particles don't matter. And it's very, very different because we don't usually think about gases, right? We've got air around us, so we don't really think about it. We deal more with liquids and solids, right? And for those, the size of the particle matters. We can calculate the density of a gas at STP. Gas densities change a lot with temperature and pressure because they can expand and contract so much. Density is the ratio of mass to volume. Gas densities are usually given in grams per liter to make them more reasonable numbers because gases are so much less dense than liquids and solids. So one way to think about the density of a gas is that it's the molar mass divided by the molar volume. And if you like to think about it that way, that's fine, and your book talks about it that way. I'm going to show you a different way too. So here they're doing examples. These are all at STP. The density of helium, you take the molar mass, divide it by 22.4. The units work out 2 grams per liter. And the density of nitrogen is going to be significantly higher because in density, the mass matters. You've got the same number of particles in 22.4 liters, but the nitrogen particles weigh more. So the density is directly proportional to the molar mass. And so you can do this derivation and end up with this equation. The density is equal to the pressure times the molar mass divided by RT. If you want to remember that, that's great. I can't remember it. I just figure it out. I'll show you how I do that. Let's do this one. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So what I would do is I would say, okay, they want the density of a gas. Density is the mass of the gas divided by the volume of the gas. So I need to find the mass and I need to find the volume. But they didn't tell me how much gas there was. That means I get to choose. And I can choose easy or I can choose hard. I'm going to choose easy. I'm going to say, what if I had 1 mole of gas? Because then everything's going to be easier to figure out. So I'm just going to choose 1 mole. I can do that because the density of a gas is an intrinsic, an intensive property. It doesn't depend on how much you have. So I'm choosing 1 mole, so N is going to be 1 mole. What's the mass of 1 mole of xenon gas? It's on the periodic table, 131.29. So the density The mass is 131.294 grams. Now I need to figure out the volume. Can I find the volume of 1 mole of gas at this temperature and pressure? Sure. Well, it's not 22.4. 22.4 only works at STP. Yeah. So if it's at STP, everything gets much easier. So my temperature, I'm going to stick it up here. 45 degrees Celsius. What do I have to do to that? I need to add 273.15. I have to put it in Kelvin. 318.15 Kelvin. And the pressure is 742 millimeters of mercury. What do I have to do to that?
Change it to ATM.
I need to put it into ATM. 1 atmosphere, 760 millimeters of mercury. So 742 divided by 760. 0.97632 atmospheres. Yeah, I underlined the wrong one. There we go. So volume equals nRT over P. I chose N to be 1 mole. R is always the same, 0.08206 liter atmospheres per mole Kelvin. The temperature is 318.15 Kelvin. Yeah, I'm getting sloppy. And dividing by the pressure, 0.97632 atmospheres. .08206 times 318.15 divided by 0.97632, 26.741 liters. I don't want to round that yet, but I'm keeping track of my sig figs so that I don't have to think too hard at the end. So that's my volume that I'm going to plug in down here, 26.741 liters. 131.294 grams divided by 26.741 liters. This is my final answer. I'm going to round to 3 sig figs. 4.91 grams per liter. Could we have used that equation on the previous slide? Sure we could have. I prefer to just use Pivnert and the density equation and think about it because that's less stuff to memorize.
It's more accurate too if we do it this way.
I think it does end up perhaps being a little more accurate. Because you screw up that equation and you're definitely going to mess things up. Any questions about this?
You said this way comes out more
Well, I think keeping track of sig figs, I think you'll end up with the same volume. I know that I'm less likely to make a mistake here because I have a hard time remembering that. I don't want another equation that I have to memorize. In fact, I only recently memorized Boyle's law, Charles' law, and Avogadro's law, and that was only because I kept doing them in lecture, right? Otherwise, I would just derive them from the ideal gas law. Did that one? Okay, so we'll save this for next time.